Um, so today we're talking about how to model a floating ring seal, which is a component on a turbopump. But basically you will learn about how you set up a problem, how you research a problem, and how to implement it in a code form. For those you don't know me, I'm a former lead engineer for 2 seasons, and I involved in Senior 1, Senior 2, Injury 1, and some Injury 2 analysis work. So if your objectives today, of course, the first thing I want to share is about turbomachines, because I think that's a pretty different topic than what our team have done before. I want to get you guys a better picture of the back end of the CFD, aka how you would actually write out all the equations and how the equations are solved in numerical form. I also want to introduce how CFD algorithms are implemented, because there's a lot of algorithms. So we look at one simple one today. And I want to show you like how you would want to implement your own model or when not to, because you will see there's a lot of work to go through this whole process. And this is basically serve as a documentation on my script. So the first thing before doing anything, what is turbomachines and the problem? What are we trying to do? So seals, of course, want to prevent fluids or gas to leak between two space. The first one we know a lot is static seals, O-rings. You will see everywhere, from bottle caps to our lovely CTI motors. Of course, we have dynamic seals too, for application that you have something that is moving, for example, a hydraulic cylinder. But now for turbo machines, that's actually a bit different and difficult. The definition of turbo machine is a device that transfers energy between a rotor and a fluid. For example, we have turbofan engines, like on our aviation jets, power generation gas turbine, turbocharger, and of course, turbopumps, the topic that we're talking today. So this is one of the common simple turbojet engine on an RC plane. First, you have some flow, you compress it, and then you go for a burner to add energy to your system, and then you finally extract energy with your turbine, and then kind of just dump everything out. And of course, this is another device that we commonly know, a turbocharger. It's basically the same thing. You have a compressor here, and then you have a turbine here. So basically the same thing, but different power source. And if we look at closely to the operating speed, you can see it's actually really high RPMs. We're talking about 30,000 RPMs. So for a turbo machine, the typical low speed is actually not that low, 10 to 20,000 RPMs. That's really fast from your common application. And typical speed is probably 30 to 50,000 and can go up to like a lot, like what we see here on the turbochargers. So, of course, the high speed brings a really big challenge in sealing, because imagine you have two servers that is having different speed against each other. This causes a high service speed differential, and then you don't want it to rub and heat, because everything will just melt. So this is a typical seal package in a turbo machine. We have a clearance seal. One type, this type is basically not really touching. We rely on a small gap. And another type is phase contact. Basically, it's actually still rubbing with a material relative to the housing. But it's really difficult and really challenging, and the manufacturing tolerance is pretty crazy. Because if you look at this NASA publication, this is for this specific seal. You can see the flatness. You need to lap it to free helium like bands. So this is an optical grade flatness, which is really difficult to manufacture from your day-to-day application. So typical size for clearance seal that we're looking at today is 2 Dow to 20 Dow. It is pretty small, actually. And the final thing is turbopumps. So turbopumps are just pump units that increase propellant pressure. That's the whole function of it. Your power source typically come from combusted gas, hot gas, or electricity. For example, the rocket electron. Some examples, this is a from the Merlin engine, SpaceX, but this is the actual designer and manufacturer. And this is another NASA pump, the fast track turbo pump. I want to give you a perspective what the pressures we're actually looking at. Typically, they're really high pressure in high performing engines. And for a typical development engine is 30 to 50 bar output. But if we look at a Raptor engine, this is a older version, you can see the pressure is above 600 bars. That's really, really high pressure. And this is another company called Launcher. They are currently, I think, acquired by Fast, another company. But this is another example of really high propellant pressure, 300 bars. But this is just the pump, not really the, not necessarily the chamber pressure. So you're going to see the chamber pressure here is actually only 300 bars, but the pump needs to be like way higher than it. A rough background of the machines type that we're dealing with. So now we talk about what is actually the design problem. So when I approach this task, I would frame it as a seal package design. That's a few considerations for my own project, which is a LOX ethanol turbo pump. One is, of course, personal project, extreme cost constraint. So I would accept a low cost, low performance design just to have something that is working. I also want to afford phase contact series because, as you can see, the tolerance is just really high and really hard to predict because you have high Q surface rubbing each other in a really high speed. And I want to minimize the shaft length to mitigate vibration on the rotor dynamic side. So based on the above, I make the kind of calls and decisions. I determine a pump turbine pump layout, basically just a turbo pump layout. I cannot really go too in depth because that's just too much to cover. But this is the actual layout. So by pump, turbine pump, I mean, we have a impeller on the most left-hand side, and then we have a turbine in the middle to extract energy. And then we have a pump impeller on the most right. And then, of course, they will be on a rotor supported by a bearing set, and here would be the seal package. So for floating rings, so what are floating rings? So floating rings basically is a clearance seal, but they give super low leakage compared to labyrinth seal, compared to the one example that we just saw. And I want to explore this concept to find a somewhat realistic performance. So this is a typical floating ring cross section. You have a shaft in the bottom, and then the ring actually ride on the shaft. So it's actually floating. That's where the name comes from. Typically, they are made out of carbon just because low surface friction, and if they rub away, they would just create some kind of powder, which is actually good because you don't want metal chunks in your system. And we specifically look at this component today, which is blocking the either liquid nitrogen or some cryogenics or the ethanol from the hot gas. Of course, we don't want it to mix because it would probably explode. So in terms of sizing a floating ring, there's a few things that we want to know from input and the dimensions. The first thing, obviously, there would be a pressure drop because we are trying to lower the pressure and then to minimize a leakage. And then we have a shaft speed that the shaft is rotating on. We have some kind of length. And then we have some kind of rotor diameter. The final thing that we want to know, of course, is the clearance, because this really dictates how much we can do in terms of manufacturing. In performance, there's two aspects. The first aspect is mechanical. It would have some kind of leakage. It would require to overcome some kind of friction torque, and it would have some steady state displacement, which we'll discover next slides. From vibration side, this actually will vibrate. So this goes up and down. So this actually also induces some kind of instability in the shaft. So why do I need a good estimate on the leakage? So the biggest thing is actual feasibility. Is can I even make this? You can see the gap is so tiny. I need to consider if it is actually manufacturable. Maybe I need to lap it. Maybe I need to have grounded. So this actually drive the design. And of course, the cost of the material. If I can get away with something that is less expensive like bronze because it's very easy to machine and is good for prototyping for this kind of component, that would be awesome. Operational, because of the small clearance and the temperature the engine would be operating, especially with cryogenics, through testing or just operation, it would change drastically in terms of dimensions. And stability wise, I also want to know where the steady state would be. Because if the steady state exceed the shaft, that means it's just rubbing, which is something that you don't want. To give it to you guys, this is how it will look like. Your shaft actually would rotate off the axis of the floating ring. So this would actually go like this, motion-wise. And now there's like 3 aspects that I want to look into, and why this drive this whole design task. The first thing is I'm making a gas generator engine cycle. So that means for the flow rate wise, typically I'm aiming 1 to 5 kilograms per second, but floating rates can go up to 0.1 and 1 kilograms per second. So for a larger size engine, maybe this flow rate doesn't matter, but for this specific size, it actually matters so much because you can see this is roughly like 10% already, which is not ideal from a power requirement standpoint. And this will require like way more flow than maybe what I have designed. So I need to at least have an estimate. For secondary loss, if there's friction torque, you may think like, oh, it won't be too much. It actually would be pretty significant and can contribute to roughly like 50% of shaft efficiency, which is pretty low. And of course, this affects the whole system balance because I need to calculate the power in and the power out. So to illustrate what I'm talking about, the pump impeller already requires some power to drive it. But your secondary components like bearings and the entire steel package will also consume power. So this means the actual required provided power would be higher. So if I design a turbine that is 50% undersized, this whole thing may not even start and work. So that is really important. And for secondary flow, maybe you think we want to minimize the leakage to 0, but actually no, because if you see here, there will be some leakage through the bearings. This is actually good because we can use the secondary flow to cool the bearings. So it's really important to understand how much flow am I expecting, because that also drive if the bearing will survive in the. So after all of those things, of course, you should define your work package because you need to go in with a clear set of goals. This is just a few objectives. I won't go over too much, but one thing I want to go over is the development risk. This would take a long time. I know this. So I limit myself to around 2 months of development because other than that, I need to focus on the big picture of the entire system design. And then, yeah, that's basically it. That's the biggest risk of this whole task. So a quick CFD recap before we dive into the details. This is kind of the workflow. We define our problem, which we just did. We kind of read publications, think about what the problem is actually about. We choose a CFD solver, we set it up, apply our boundary conditions, meshing, blah, 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 blah. However, everything will be done in one script today because it's a pretty self-contained problem. And of course, this is an important concept too. Nothing can be described as perfect as, mathematical equation. So common example is just in Minecraft blocks. We disperse that into small chunks that we can manage, which is called control volume in a numerical sense. Dynamics model, our typical one would be Navier-Stokes. That's just good to know. And then we solve our system with some kind of approach of a solver. Very important thing to mention is all models are wrong, but some are useful. And we'll see if the setup and the script I made is actually useful at the end with validations. So to do literature review on the floating rigs. So the first thing is, where do I find most literature? So this is actually a tribology design, which is pretty interesting. Another thing is a tribology thing, because tribology is describing thin fluid themes. So this is exactly the problem they will look into. And in terms of problem, there's two types: fluid versus gas. We look at fluid today, incompressible versus compressible. Even for fluids, because the fluids compress really high pressure, so they are somewhat compressible at that operating range. So sometimes it's really important to model that too. And finally, I think some of you may know single versus two-phase flow, which is really difficult to handle. So we'll just do single flow today. Use auto model through like commercial modeling, empirical equations, but they don't really capture the thing that I really want, especially how the eccentricity changed the leakage. So finally, I selected two main reference. Basically, the first paper gives the best explanation of how things are implemented, but the second one is more intuitive to understand. So because I don't know really anything, start off this project in terms of implementation, so I just go with the easier one first. But that's caused me some trouble, which we'll look into in the next slides. So the model, what is the model? The model we're using a bulk flow model, meaning we're not really modeling the 3D effects. We're only modeling the kind of 1D effect. Oh, so that's fine. So what I mean by 1D flow is we will have, like, if you know fluid velocity profile, it will look something like a curve. So instead of the curve, we'll just take the average, which is something like in a pipe. So this is just a coordinate and the picture. Keep it in your mental mind, because we'll reference this kind of geometry a lot. So talking about the swirling motion, the shaft actually rotates like this. So this is actually a transient simulation, which is quite difficult. And this is the set of equation that describe it. And you can see some time-dependent terms. So because it's a time-dependent solution, which is difficult to solve because we have to do time marching, we apply a technique called perturbation. Basically, what perturbation is doing is we approximate the solution by separating. Imagine we have an actual solution. We decompose it to the steady part. So we call it zeroth order, which is something like this. And then we have a first order expansion, which is this set of equation. And then we have a truncated error. One thing to know is this involves complex numbers. So this is really tricky to implement to make sure you're right. A side note, this is called Einstein notation. If you are taking advanced materials or something, you will see similar equation form. This is just a compact form to write out tensor equations. So a few comments. My script implement the absolute form, which means I use actual dimensions. Technically, this is not good because everything would be really small numerically, which could be down to your machine precision, aka how low your computer can model. So this caused some trouble in terms of coding. So we have a set of equation. Now we talk about the simple algorithm. Is semi-implicit method for pressure length equation. And simple is just one of them. There's a lot of them. So why do we use this set of equations? If you want to know more, check out this two textbook, really good textbook. The second one is very good to read. It's pretty easy to read. So simple is just one of the algorithm of this family. You may heard like simpler, simple, consistent, or PISO. This is really common. And typically we have a system, of course, as the name suggests, have the pressure and velocity coupled. For example, we have this equation here. You can see we have some pressure terms, pressure gradient, that drive the velocity of the rest of the system. And then, of course, we will have a continuity equation to make sure everything goes in, everything comes out. A very high-level procedure, ignore the equations, will be we first solve the momentum equation with a gas field. So everything here is just a guess. But this momentum equation actually follows the continuity equation, which is fine because we will correct it using the momentum equation. We'll find the actual error and then correct it. This is called a prediction step for solving the momentum equation because we're just predicting. And then we have a correction step, which we will correct the rest of the quantities. We discuss like super in depth. So this is just high level procedures. This would be a really, I would say, math heavy, but I try to make it as easy to follow as possible. So let's look at the equation first. A close look. Of course, they're partial differential equation PDEs because everything partial forms, and then it depends on the actual direction variable you're taking derivative of. And actually pretty similar to the Navier-Stokes equation if you look at it. We have a continuity equation, we have a pressure terms, we have some transport quantities, convection quantities. So it's actually really similar in terms of the layout of the equations. Do we want to discretize our system? We want to recast the analytical form in something that we can write out an equation of. It would matrix form in terms of we have some kind of coefficient matrix with our unknowns and some kind of boundary conditions or known variables. And basically want to determine how we would build the coefficients of our algorithm. So now the first step, if you're taking fluids, the first step, of course, you do is you make assumptions and then you try to simplify this whole entire equation before you do anything. So that we can do is steady state because we're just solving the zeroth order, which is for the perturbation. So we have no time derivative terms, and then we also assume incompressible for this particular problem. So that means we can factor everything out here too. So after everything, we come down to this set of equation, having no time dependent terms. Everything is just steady state, which is relatively easier to solve. And for finite difference, so this is a pretty important concept. If you're taking computational method, you may know this. Imagine we have a function, a random function. How do we take limit? The limit would be using the limit definition. So we assume we have a point x here. So the slope will look like something like this. But you may ask, like, how do we take actual steps? So if we do one step forward, we can take a approximation here. So this is actually called a forward finite difference because we're taking one step forward and then just take the 2 point here. Basically, we just rewrite the limit definition. But we can also do a backward step. And then we have a backward finite difference. Basically, just substitute this in here and we get the same thing. And finally, we can also approximate taking between with these 2 points here. It will look something like this. And you will see, it's actually pretty close to what the actual slope is. So this is called central finite difference because we're taking from both sides. So a more formal way to find our discretized form would be with Taylor expansion. Basically, just expand this function around a particular point, which would be here in this case. But this is not a form that we want to use because we want to express everything in terms of how small everything is discretized to. So we substitute this in here and we will get this equation. So we call this first order expansion because we just order to first order with n equal to 1. And then this, but we'll ditch it. So our error term is to the second order. And this is called the big O notation. If you're in comp sci, you probably will know this because this is a big topic in terms of computational complexity. So what is the error of our forward difference for a finite difference? We basically just rearrange everything here to the left-hand side because this is what we want. And then we divide by our step size here, and we'll find, oh, it's the order on the order of our step size. So this is called the first order expansion, first order error. And of course, if we want more accurate, we can either use a smaller step size to do a better approximation, or we can write an equation with a smaller error term. That means with the same step size, we'll have a smaller error. So there's way more to discuss on this topic. So just remember this and then this form because we're used a lot of this. Now so on the previous slides, this would be, we would call a grid because we're taking finite points. For a simple algorithm, we actually need to use another more special type grid called static grid. Imagine a grid like this. All the big points here is the pressure ones. And then we have some kind of velocity components. So this would be our X component, for example, and then we would enclose it with a control volume. So this would be our X momentum control volume. And then of course we have a Y component. So we have a Y momentum control volume. Finally, we have a continuity control volume, or it's more to store every other, oh my God. Okay, we have to do that. Every other different properties like pressure or fluid thickness. Actually, I just finished this side. So because it's really confusing to use up, down, left, right, we just use a kind of directional reference. And if we take a look at the continuity control volume, it's actually really easy to calculate our continuity because all the velocities are actually live on the boundary already. So we simply just add there. So you may ask, why using a staggered grid? Why the velocity and pressure is slightly offset or between each nodes? So imagine you have a pressure field like this, which is highly nonlinear with jumps. This is called zigzag. And then we take a control volume like this, and then assume we take the midpoint value here to find our pressure differential. What you will find is we say we have no pressure differential here, which is super unrealistic, right? Because this is so massive. So you expect a dip in terms of the change. But from our discretization, you're saying there would be no pressure differential, which is completely wrong. So we have to take pressure at the nodes directly and then use the velocity at the boundary. So this is just to keep in mind, this is not using simple. This is just to illustrate. So now with the grid that we just specified, we now will write our equations out in a pretty easy to understand format. A few simplification again. We'll use uniform grid because what does that mean is we have some kind of length. We simply need to divide by the number of chunks, which is nice because this is a constant value. So we can factor everything out and not consider the change between the mesh. Of course, in a typical CFD, you would use a non-uniform mesh because you need to capture important details. But for this, it's actually a difference because by unwrapping the rain into a 2D sheet, it's just a 2D domain at the end. So it's really just better to do a uniform discretization per axis. And then to take finite difference, we will use unwind, which we'll see what I mean by that. So on a grid, a few notation-wise to keep in mind. Notation is actually the most difficult part on the entire project because there's just so much things to keep track of. So we have a center node, center velocity of set momentum. And then we have some neighbor velocity. And then you can see the theta velocity actually lives on a slightly different grid because by our staggered grid convention. So to take this actual that is live on the set momentum control volume, we have to take a approximation key. Finally, we have two pressure quantity across this cell. So momentum equation, we will discretize like this. So first, of course, we'll say, oh, this is what we have in this control volume. So this is Uij. Now we take a finite difference, but we assume the flow always from west to east. So this is just a first order approximation. We'll discuss more why this is good or bad. Again, we'll take this partial differential term of the pressure, also using finite difference, just first order. Just simply take this, divide by the grid size here. So we have to approximate roughly what this looks like because it's on a different grid, different control volume. So simply take the average of four corners. This one, this one, this one, and this one. And then for this term, basically the same thing. We're just taking a finite difference across either using this one or using this two. And this depends on if the flow is flowing from north to south or south to north, because we want a term that drives the flow. If the flow is going this way, we want this to be the dominating one to affect this solution. So that's why we write as like slightly different. So now we have discretized the most important terms. But remember, we still have some other terms that we don't really know what that is. And you will see this equation is actually nonlinear because this is nonlinear, everything else is nonlinear. You cannot really write everything out in a matrix form, especially with like squared terms. But remember, because we're doing iterations, so that means we can simply take the previous iteration to kind of fix it. So everything here would become constant, and we keep everything in kind of like first power to keep it linear. And a more official term is this chunk here, especially for these two terms, is called convective flux, because this is actually from a convection term. So remember, we have a grid like this. So now we can write out the whole equation now from different kind of coefficients. And then simply we can put it in a form like this. So now we have a linear equation because you can see everything is first power. And if I want to write a matrix form, I can write, extract this 4 out of become a column factor, and then this would be another factor. And then we have some kind of condition at the right-hand side. So if I am going to do it for the theta side, of course, we would basically do the same thing. And then write out this equation in the same thing. And one thing you will notice is the set momentum and theta momentum is actually independent of each other. We don't have any theta terms that is like active in this iteration because everything here is unknown. So now how we correct our errors per iteration. So remember a control volume like this. The correction we would call, we have a true solution, and then we have a correct current field, basically current iteration, and then we have a correction field. So if we rewrite our previous equation in this form, just summing up all the neighbors, and then focus on the center node, and this is just our pressure differential term. And then if we substitute, we get this form. So we say the correction, the difference, the error term is actually just this with this error term. But now we don't know either of this. So we work on finding this guy here. So what's the neighbor terms? They would be assumed to be 0, and I've just neglected. Why is this true? Because as the solution keep marching, our solution would keep better and better. So basically this minimized because this error term minimized. So this is correct. Why this is correct? So if we just reassemble again, a lot of kind of algebra here, but just whip this guy here and we get this equation here. So this is our correction equation. And we call this just D. I don't know why they use D, but it's pretty common to use D. Same thing for the theta term again. So now, if we look at our continuity equation, because this step we're solving the continuity equation, and we'll simply just look at the set term. So if we write the set term out, we can again find a difference, add the boundary, because notice we're taking also the thickness too, because we need to take whatever mass in and whatever mass out. So this is a flux term actually. Now one single thing, we'll see, we should just substitute this U equation in here, and then substitute what we just find here for the correction term. And then if we expand the whole thing, again, rearranging everything here, we'll get an equation like this. So now everything is written in a, pretty consistent form, which is center cell plus some neighbor cells and plus some known quantities. Ideally, we'll simply correct everything with what we just found error-wise. However, this is not the typical case because it would diverge if the step is too large. So we induce a term called under relaxation, which is simply how much we correct. Of course, 0 to 1, and if you have above 1, it would be over relaxation, which is just speeding up the whole solution. For the momentum equations and velocities, we will just write like this. We'll take some part of the old solution plus the new one that we just find. Same thing for theta. Just a reminder, this is what the correction term looks like. So now we have set up all our equations. Now we're actually going to solve it. So we need to switch our mode in thinking in matrix form. Resemble something like this. And mathematically, if you want to solve this system, you will simply insert the matrix and multiply here to find your actual quantity of your unknown. However, this is really expensive. If you have an n by n matrix, this requires cubed operations. So a 1,000 matrix requires cubed, which is like really massive. And for a CFD mesh, typically we have roughly million nodes. So those numbers add up really quickly. So in practice, basically everyone use some kind of iterative solvers because that's just way faster than inverting the whole matrix. And we'll look at a very simple and common method that you will actually learn in class if you're taking computational methods. So we have a equation like this. And then we divide our grid or mesh or domain into this intervals. So because this is a boundary condition, and then this is periodic because it's wrapped around. So if we write our equation in a matrix form, we'll get something like this. This amount of unknowns. So roughly your domain size, just like how many points you have. So with that much unknowns, we have a column factor this size. But how big would this coefficient be? It would be squared. So that means N3D would be whatever your domain points are, would be roughly squared. So it would end up being a really, really big problem to solve, even with computers. So this gives you the perspective how big the numbers could be. So a really common, easy to understand method is called Gauss-Seidel method. This is a iterative linear solver. Here's successive over-relaxation in a script. But basically, the core idea is using this method. And in full matrix form, we take squared per iteration. You may say like, oh, it's only one power off, but one power off is a lot actually already. And this is actually pretty poor performance-wise in the computational world, because usually you want a true linear solver, which is just ON. But this is a pretty easy to implement one. So remember, we have an equation like this. So to find a particular solution on one component, we can just substitute, move the AP over here. So if we look at a point, if we look at 1, 1, because we know the boundary condition here, so we can solve this equation. And then after we solve 1, 1, we substitute to the 2, 1 equation, which is here. Now we know it. Everything here is a guess. Remember, we're guessing this one's, but we know this one. So we solve it, guess this two, solve it, plug it in, do the thing again until the end of your matrix. Keep iterating until it converges. So that's the whole core idea of this method. If you want to look onto this is a more formal way to write it out. But basically what it's saying is just for a particular solution, we will subtract everything that we guess from something that we know. But that's basically the meaning. And we'll have a relaxation factor like this. Sometimes it would diverge up. This is kind of like illustrating the computational speed. There will be some kind of optimal, but you never know that until you actually solve the system. So if omega is bigger than 1, we call it under relax. Because why it's called under relax? Because you're taking like a bigger step. So you have faster convergence, but it could diverge like this. If we take, of course, it would be slower, but it would be stabler. And now it's a good time to show you the code, what I mean with the fellow. So this is the script. The only thing that will change here is this fellow here. So this is the relaxation coefficient. So we're gonna start with like 0.8, which is under relax. So we'll solve it. It will take a while just for the first computation. So okay, you can see for 14 iteration, we get something. Not necessarily right, but we get something. So now if we speed it up a bit more, like 1.2, do the thing again. Okay, it still gets something. We don't know if it's right or wrong, but let's just get something. And if it's the kind of required iterations. So 47 only. But this is a 31 by 35 system. So that means if we take the full matrix form, it would be really, really large. And this is actually way faster than what we have here. Now, if I really want to speed it up, maybe I do 1.6. You start to see some problem. Oh no, what happened? So basically what happened is it explodes, it diverges. So now you get nothing because it's undefined. Maybe you get something like, oh, something 1 defines 0. So this is the problem with like way too aggressive relaxation, is you will get just simply you would diverge. You won't get anything from solving the system. Oh, change this day. So now going back to our final procedure. In recap, we have some prediction step, we have some correction step, and then we just throw it into our linear solver that we just saw. So now, finally, we can do some boundary condition and initial guess. We cannot cover too much because it's just super in-depth math in terms of writing out the equation. But it's just really good for you to know what is going on. Boundary condition, we have a pressure differential, we have some kind of shaft speed, we have our grid here. So we apply a entrance pressure. However, because we have a shaft step here, so we model it with a pressure loss term. It's basically what you would see in your fluids, just like a factor. And then on our boundary, we also need to specify how fast our feeder velocity is flowing through, because your flow could have some swell. Swell is just a component of like tangential velocity. And notice the pressure and the velocity of the actual flow change per simple loop. So they are not really boundary. They are boundary condition at a sense, but we are also solving it per loop, per iteration. And then of course we have a downstream pressure at the end of our boundary. And these two boundaries have the same value because they are periodic, because we're unwrapping the ring. Initial guess is really important, because if you're really close to where you want to go, you would, you can look at it. Versus if I stand in the ferry terminal and I want to go to UVic, it's like way more difficult, right? So the first guess is pretty important. And we do need some kind of guess. So I simply just implement a linear model from some empirical, I forgot how they get up, but the equations are like this. Basically, it's just the overall delta P across the sail, and then with some kind of velocity. So I just solve this and then get my initial guess. It doesn't matter how close this is, because we just need a good guess, and this would be a good guess. Now is the most exciting part. It's the Python. So we actually code everything, implement it. So before proceeding, again, we skip some really important treatment that we won't go over, but they are one of the key points of the iterations. We'll repeat all the procedures for the first order equations, but we just talk about serial order, and we'll only talk about the most important implementations. One thing to note is Python is definitely not the best choice, because Python is really, really slow compared to all other language. Actually, it's probably like the slowest for a lot of things, because it's not compiled, it's interpreted. So organization, I want something that can be called simply as a library, and as the end user, you should only think about how to use that, and you don't think about implementation. And basically, I would just create a Python package, and we want it to be modular and easy to trace. So this is the overall structure, pretty common for any Python package you will see. This is just another folder for some compiling with a library. And then if you look at the setup, this is simply just all the data class here that allows the user to define the operation range and the mesh and everything else. And solvers, this is the main actual file of all our CFD code implementation. So if we look at the code itself, two classes, because we have what, zero and first order solver. So pretty intuitively separate it first to make it self-contained. And one thing to note is the first order solver take the zero order, so that's important to recognize. Two class, this is actually not that many lines, thousands. Yeah, that's not that much. And we'll break down the steps in the method because you want to be very modular and traceable. By methods, this is a more specific term in Python. So this is the entire first zeroth order solver, which is just a bunch of subfunctions. And you can see, even for just one single solver, we already have like a handful of subfunctions. So organization is really important, and remember to commit over on your GitHub to make sure you save everything so you can go back if you mess up your script, because you will mess up your script. A simple loop. Yeah, I think Ryan can relate. So again, look at the simple loop again. So this is the implementation of the loop. So we first initialize, and then we solve our step here. We build our coefficients, and then we just solve our equations. And then we have a pressure correction step here. This is just correct the boundary conditions and other quantities. We don't have any other transfer equations. If you have, it would be like temperature, whatever energy you're considering, but we don't have it here. And then finally, we check the convergence. One thing to know is really important to set a maximum iteration, because you don't want to set like forever, because it will just run forever. And oftentimes you won't get anywhere if you if you don't even set a range. So always set a range so it will stop at least. Now, building coefficients. Again, we have this set of equations. So simply, we just type it in here. Hopefully, it's somewhat recognizable in terms of the form. Here we have this term here. Basically, this function is only dedicated to build all the coefficients for our grid. Now the linear solver. So going back to the successive over-relaxation method, this is the actual algorithm. And then this is the loop. So here, you see we apply a kind of a non-zero zero. The thing that we want to prevent here is we don't want any divide by zero, because of course it would return something impossible for us. It would be just NaN. And then this is to check the residue to see if it met our threshold. One really important optimization that I use here is using the number library. So this entire function is constructed under the number umbrella. So this library is used to increase the computational speed by a lot. It allows user to compile certain functions, not necessarily the entire script, in a way like C or C++. One really interesting thing is it does not require any compiler. So you don't need to install any C++ compiler. You only need to call this library. This is called a just-in-time compiler. So when it runs the function the first time, it will compile it and it will cache. So it will be really, really fast. And this actually can approach C or Fortran speed. Fortran is like the goal of computational speed, just because how fast it can be. And it's really low level too. A few restrictions to mention: it can only use on certain functions. Not every library can be used on this. And you can only use certain data types as all your Python functions. There's some limitation, and it requires a bit more structuring in your code. So when you start out, probably don't use this until you know what you need to optimize. So now I want to give you the perspective how fast things are using this library. So on the left here, we have a pre-optimized, and basically the two code are the same. It's just between one commit. The only thing that changed is if I implement number or not. So let's run this first. You can see I'm using a pretty high mesh count. So now we wait. It could take a while. So there's just one step though. This is the first step. So it saw the function first. So now it's compiling it. It took how long? 16 seconds. Okay, now we wait for the second one. Probably another 16, depends on how fast the convergence is. The main thing I want to show you is the second one, because the second one will show you how fast this actually is. Right, finally, it done the first iteration with like 45 seconds. With a pretty low mesh count, because it's only 150 to 150. So now if we look at the second time, it is using the number library now. Now we keep waiting. This is still Python. So we stop here. You see, 20 seconds for the tune. So this is really slow. It's like too slow. You cannot do anything at all. And then look at this number implementation. Only thing that changed is the linear function. So like it's like splitting out everything. And if we look at the time for the required, this only takes 50 milliseconds per run, and the first run and the first one compiling only take 1 second. So we go down from 45 seconds per iteration to less than a second per iteration. So that's really big optimization that I suggest anyone who is working on similar problem to implement, because you don't have to wait for like 2 hours to get one thing. Sometimes you need it, but for this, if you can, always implement it. So now validation. All models are wrong. Is this one useful at all? You want to validate first. The thing that I would want to know typically for a solver is how it behaves, because every solver is slightly different. And I also want to see mesh convergence, if the solution actually converge, and any unexpected behaviors. Of course, start with a sense check. Simply, it's just get a feel of what the solver actually does. And by that, I mean, literally, simply, just put something, just to see what happens. So I won't, I haven't plugged in my capacitor if I plug in my computer. And the tip is always plug in your computer if you're doing computational stuff. You never appreciate how fast your laptop would be if you plug it in. So this is just a script. So the first thing that I plot is just a pressure plot. Does this make sense? So we check. Nothing is lower than 0, which is good, because nothing should go under 0 in our assumptions, especially for this particular model. And actually, for the first few implementation, I get negative pressure, which I know is wrong. So that's how you debug your script. So this is a kind of just deviation plot. We're comparing to the mean value of each column. So we're just comparing the difference in the theta direction, in the z direction line. So we compare like vertical. So does this make sense? This kind of makes sense, because pressure should be pretty low on where the ring is like squeezed, because there would be eccentricity, right? So we would expect somewhere we have high pressure just because it's pressing on it. And then we expect lower pressure somewhere. You may ask, why why do we see like a somewhat diagonal? This is because the velocity, we have some swirl velocity, right? So the flow is actually going this way too. The total magnitude going this way. So this kind of makes sense. But is this actually how the solver behavior is though? So a quick change that we can do is simply look at no swirl. No swirl means at our boundary condition, we have no theta component. So we run on. Now we use this thing, just want to show you, this plot here. So you will see like, oh, it's less severe now in terms of the distribution. But you see, there's still some diagonal velocity. Why? Because the rotor is rotating, right? So when the rotor is rotating, it's actually drag on the flow. So the flow would have a theta velocity component at the end, just because of the motion on with the shaft. So the last check, of course, is to ask ourselves, what if I do 0 shaft speed? What would you expect under 0 shaft speed? It would be a somewhat like symmetrical plot, right? Of course, numerically, we cannot do 0 because it would be divided by 0. So I just make a very small velocity. So now this is the final pressure plot. And we can see it's symmetrical, which is exactly what we expected. So this is how I check if the solver is behaving like at least some physical sense first. So this should be done before any further validation, because if you cannot get this step right, you will get nothing right at the end. And here is just like some more plots to help me to think about how, if this is correct in terms of the solution. So now we get into the actual validation in terms of the leakage. The first one, of course, I just use the main reference because they already have calculation result. So it makes sense, right? Because you're implementing their method. Of course, you want to check if is it somewhat close to what they're doing. No, this is not a test data. This is just they're using liquid hydrogen in their analysis. So this is the plot they have. This is the plot I have with different mesh size. So this black one is this one. So what do I see? I see convergence because you can see the solution difference start to become smaller and smaller. The trend is like pretty good. It's pretty consistent. Maybe some end term is a bit different, but that's okay because that's probably just how I discretize things. One thing interesting is you see a rough mesh seems to perform better. And is this actually the case though? And one thing to note is convergent doesn't mean accurate, because you can see the solution is converging, but it's actually more and more wrong. So this is a important thing to keep in mind for any CFD. You have a converged solution doesn't mean you have an accurate solution. So now the second case, I just use the other paper as reference. The test is a test data with water, which is nice because it actually tests. And validation, mainly I want to focus on the mesh size. If it's actually the rough mesh is better. So few plots, 30, 50, 100, and 500. And trend-wise, it's overall pretty acceptable because the error is actually pretty decent with a rough mesh. And we can see the lower shaft speed seems to deviate more at like this point, which is pretty consistent across all the solution. And then now, maybe I can start to say coarse mesh is actually not a fluke. It's actually how the solver behaves, because the two test points are so different. But the final one, this is also another test case with water. Just plot the same thing here. And error-wise is pretty consistent. You may think, oh, it's pretty big. But for such a simple script, simple as in relatively easy to implement, it's actually pretty decent because it's within what I actually want and can accept. And trend is still really consistent for all the case. One last thing I ask myself is, does dimensionless quantity refer to anything? For example, we typically use Reynolds number to quantify if a solution is or a problem is similar. Not really, because I don't really see anything. For example, this is the two case that I show here. The first one I compare is just Reynolds. You can see it's completely different, off by like a magnitude. And then for other more specific, problem-specific dimensionless quantity, we don't really see any like similarities. The one thing that is like somewhat similar is the ratio between the clearance and the rotor radius. However, this is the only thing that really is similar. Nothing is the same, basically. Of this validation, mesh size, keep it rough, because for some reason, coarse mesh just works better for speed and accuracy, as we saw. And max deviation with like the test case is like around, usually under predict side if I use a coarse mesh, which is around 10%, which is okay, which is something that I accept in my system design. Computational speed wise, pretty fast, around 1 second per case. So that is like per design point. It could take a while if mesh is too fine, just because it's harder to converge, it's more solution to solve. And overall, the zeroth order implementation is, I would say, is pretty successful and useful, because I now can actually spec a floating ring soon. But how system? We did not talk about any of it. So I actually implemented, but unfortunately, I do not get anything realistic. It's off by a factor of 10, but somewhat numerically, number-wise, it's like close. But it's just a bit weird. So, of course, I won't use it. Some possible errors is just how I interpret the system of equations, because it's with complex numbers. It's a bit difficult to handle. And I could be just taking the final difference a bit off in terms of the required accuracy. So, and I also may have to implement dimensionless zero order equations to properly use the two equations. So, of course, I did not do it. We have to mitigate this risk. So, the zeroth order told me only 21 days from learning everything here to implementing. So that's quite a long time already. And then the first order told me another 13 days. So by the 13-day mark, I know I won't make it, because it's approaching the 2-month limit I set for myself. So I kind of just accept the fact that I won't get it within 2 months. So I just, take the time to work on validation, at least on something that is important. And the first order, zero order is more important, because that's actually the thing that would drive the actual design in terms of the overall turbo pump. So that is the conclusion of the first order system. Like lower priorities aside sometimes, because the more important thing is having an actual design layout. So now we wrap everything up. Lesson learned from technical wise, personally, CFD implementation. I never thought I would actually do a CFD implementation, but it's like, too much after this already for CFD. Pretty advanced fluid knowledge, because it's a really different field in terms of fluid mechanics. And really in-depth rotor dynamics, review, like vibrations, Python. I'm pretty fluent now. So if you guys want to get fluent on Python, just do something crazy with Python. What not to do? I won't use dimension equations again, because think about it. If you solve one dimension equation, like for example, a Reynolds number, you can simply scale it up. It could scale up. So that's actually way better for numerically, because maybe you only need to compile one case, and then you can store that case and then just reference it in the future. Some improvement that I would do to the script is more optimization on speed, because I can use number to parallelize even more equations, especially when solving the U set and U theta, because they're independent. Linear solver, probably do something faster, maybe assemble it in a form that I can use a particular algorithm, there's actually order of ON, which is like super fast if you can use. Discretization, probably a bit more use different scheme because we only talk about outline, which is first order error. But maybe I can implement something with a lower order error, and then that would give me better result and accuracy. Assumptions, again, I assume incompressible flow, but if I want to do it with gas, I do need to implement a compressible form, which is just rewriting the equations. So closing remarks, some final tips. If you're doing something like this or any problem, or actually on any problem, is your majority of the time should be on understanding on the theory well. You should be able to look at what is code and then deduct like, oh, this should look roughly like this. Does this make sense? That's really important. And you don't need to be a postdoc level to have a good grasp of advanced theory. I'm still an undergrad student, but I can kind of explain to you some graduate level knowledge already. Is it accurate? Maybe a bit off, but is it useful? It's pretty useful. All models are wrong. It applies to all your engineering problems. I guess like everyday problem too. You have to think about, is this meaningful? The first thing I ask myself is, should I spend that much time on this? And of course, the next one is think about how much time I should spend on it. You should also think about impact of your work at a system level. This work allows me to size everything else on my system. So that impact is really important for trade-off and sensitivity analysis. And you have to be prepared when things don't work out. For example, I know I may not complete the whole thing. So I just accept the risk and then just mitigate it by, okay, we'll come back to this later, but get the more important things first. And make it work first. If you don't make it work first, why optimize? Maybe you're just optimizing the wrong thing. So just make something work first. And always assume you missed something. At least that's how I carry on this whole project. It's just I assume I miss everything. So in summary, what we covered today, that's a lot, is some turbo machine knowledge, a problem, CFD implementation, especially on simple algorithm for the pressure velocity coupling systems, some numerics, basic numerics, finite differences, and linear solvers. You can probably read computational publication pretty, at least know what's going on. Now, we also go over Python implementation and the optimization. Remember the 50 times speed up. That's really important. And how you validate a solution. So now you can make some simple jokes because you know how the simple algorithm works. So I know this is a really heavy technical presentation. So thank you for your focus. Yeah, hope you guys enjoy this. And if you have any questions, just let me know. Yeah, thank you. Yeah.
How do you get your fluid properties in the script?
So yeah, that's a really good point. So of course, because it's a incompressible flow, I get the let's use this. I get the properties, just true prop, of course. That's something that I actually need to look into because I'm taking only upstream density now. But maybe I should take midpoint density and temperature. So this script assumes isothermal, which is same temperature fluid flow. So I just take upstream pressure and temperature, and that's basically it. But for a changing, for like something that changed a lot in terms of fluid properties, something like this, you can see the difference. Using a variable property gives you like way better result. So if I would do it as a code form, what I probably would do is either use a approximate equation, Runge cutter, not Runge cutter, but like that one, or just cuprol. So write in equation form. And one thing to note is fluid properties matter so much that it actually affect
the rotor dynamics part too. Oh my God. I think it's this one. Yeah, hell yeah. So this is the result. And you can see this part is the constant property, and this one is the um, variable property. So you can see this actually is better because this also captures some instability of your system, but the constant property won't. So this is also another risk and error in the script. So the script is more focused on the leakage, but for rotor dynamics, I have to put in like way more validation and work on this.